Hi everyone, very good afternoon. My name is Anup. I'm a manager at Digitode Technologies, Bangalore. Thank you everyone for joining in the newest edition of our webinar series organized by Digitode along with Digilent. Now, today's session, we are going to be focusing on SDMI, TDMS, and deep neural networks implementation on PYNQ Z1 boards from Digilent. But before we get into the webinar, I would like to give you an overview of Digitode and what we do. Now, many of you would already know that we are a leading provider of industrial, academic, and research solutions, specializing in test, measurement, industrial automation. We're also very good at 5G and 6G wireless technologies, AI-driven IoT solutions, and quantum technologies, along with advanced robotics. So these are the OEMs that we work with. We work with ST Microelectronics, Digilent, QU Tools, QBraid, Advantech, TMDS, Mantis Wave, and Crobot Technologies. These are our authorized OEM partners. And the key solutions that we work with our clients are listed here. So we specialize in quantum and optical solutions. We do high performance test and characterization systems for quantum tech communication, fiber optic networks, and photonic devices. And we do wireless testing, prototyping, and research solutions, enabling next gen communication technologies in FPGA development and VLSI design. We do verification and prototyping for advanced computing and hardware. With AI and machine learning, we have solutions in Edge AI, in AI OT, industrial IoT, and vision AI workflows to enable real-time intelligence in embedded applications. And when it comes to automated test and measurement, we do end-to-end solutions in sensing, data acquisition, and we also build for high performance real-time monitoring across industrial and academic applications. All right, I would like to hand over this session to our speaker and our FPGA design engineer, Ashutosh. Ashutosh, over to you.
Thank you, sir. So I will start presenting my screen. So welcome everyone. I'm Ashutosh Tiwari. I work as FPGA design engineer and digital technologies. I work closely on lots of Digilent boards, and Digilent is an NI collaborated company, and I'm going to discuss this webinar is going to be about how you can implement an artificial intelligence image processing applications in Digilent boards. Very low cost and low power devices. How can we use it to achieve such kind of optimization? So we as Distro Technologies, we work closely on industrial solutions, academic solutions. We have a lot of research solutions also. We have worked closely on FPGA integration for wireless applications, and image and audio processing is completed from all the Digilent boards which we have going to demonstrate for now. So this is the main board which we are showing or doing the processing of the system. So ping Z1 AP SoC. So in the left side, what you are seeing, this is the Zing 7000 processor, a standard processor which is present on all FPGAs or an inbuilt application for all Zing 7000 ARM Cortex processor. So ping Z1 is an AP SoC. So AP SoC is an all programmable SoC. It has two peripherals. One is called as a programmable logic, where you can write your own RTL, you can write your own displayed codes, and you can design lots of own logics. Whereas PS side is something which is controlled by the processor. So processor, once we are trying to control the processor, means it has a lots of master to slave connection or relationship, which is called as AMBA or interconnect. So AMBA is the protocol where you can connect your processor and implement a slave to master relationship. So this is the ARM Cortex, which is the slave, and this is the master processor, which can be used to integrate the processor IO mux. So FPGAs basically consist of three blocks. One is the input output blocks, are routing interconnect, and the logic cells. So this is the AP SoC or the zinc processor, which we are going to demonstrate. And this is the HDMI output pin, and this is the HDMI in pin. So source to sink integration, how you can implement in a simple Z1 board. This is the Ethernet port, which is used for communicating or interfacing with the network. So the real-time network or interconnect connection can be done through the PS side of the PYNQ Z1 SoC. So along with that, this is the audio output. It has an inbuilt PDM. So PDM is an pulse density modulation. So based on the audio signals, whatever it is receiving, the PDM, we are channeling it and we are trying to give the audio output through the PWM channel. So this audio out is can also be called as a PWM channel. This is the general purpose input output where you can integrate your camera or a sensor or some Visual Studio's sensors can also be implemented through this PMOD or peripheral module. So the main application what you can implement in PYNQ Z1 is the HDMI input output, the USB host, and your Ethernet port. So the first thing what you can implement in PYNQ Z1, uh, the main agenda of PYNQ Z1 and why it is more greater and a very good SoC is because that it has both Python language and VHDL language supporting. So the PS side, you don't have to write a code for PL. You can directly write a code on the PS side or in the Python side to implement the deep neural network or a DNN for object detection or recognition of pattern. So what is a deep neural network? It is basically inspired from brain neurons. Whatever the patterns what we give as an input, it is going to detect it by containing which where it contains a lots of hidden layers and the propagated weighted sum of input data to output data. So whatever the input data the camera is taking, it is going through a hidden layer. We are trying to implement a hidden layer topology in Python language, and you are trying to get the output in through the camera. So the detection or the result will be given by the camera. So we also have a threshold. Once the threshold is crossed, whatever the output what we are seeing, so let's just assume that this is a person, this is a car. So the detection is happening based on the threshold. Once the camera is understanding that yes, this is a person, and the value of that sum or the weighted network is greater than that threshold, then it is going to detect it as a person. Or if the value of this threshold is more than this car, means it is going to give the output of the car. Which this is the response which you will get from your Z1 SoC. So once we understand the difference between the pattern and the input data to the related output, it will be very much easier and it will be very simple to understand what is a deep learning in PYNQ platform. So facial recognition. So a very important application in all surveillance team, what they use is a facial recognition in PYNQ Z1. So how can you implement such a facial recognition pattern and bring a label for this particular output? So I'm going to show you a demo before I start explaining this facial recognition, because it is better to understand what is the facial recognition in the output before you go through the theoretical part. So you may see here, this is two output what you are seeing. I hope this screen is visible. So one name you are seeing is Ashwini and another you are seeing is Ashutosh. Whereas once the threshold is crossed, the threshold whenever you are seeing, I hope I'm going to show you through the board. So yes. This is the FPGA which we have used. This is a USB host or the USB camera, what we have taken. This USB camera is connected to the top side of your module. This is that module or the camera where I'm giving my active resolution output of my Z1 SoC and I'm passing it directly to the HDMI. So if you go a little bit closely, you will see that my name is displayed on the screen. So this is the accuracy what we are getting. My PYNQ Z1 SoC is trained in such a way that it is going to display my name as Ashutosh, even after it is getting some kind of unknown. But whereas if it is seeing another person's image where it is not facing, is not recognizing that face, then it is going to show you as an unknown. So the main difference between the detected image, I mean the trained image, what we have trained in PYNQ Z1, and what is the unknown image. This is a very important application which can be used in surveillance or attendance monitoring, and all other applications can be implemented through this very simple application. So once the frame rate is decreasing, it is going to detect that the threshold is crossed and it is going to find the output. So what facial recognition input what we have given, it is just from the HDMI port. So I'm going to show you the code or the code before we proceed with the output. So yes, just give me 1 minute. Yes. So this is the code where I'm getting the output of all these variables. How am I getting this output and how am I implementing such a facial recognition module? This is the every instance it is trying to detect or grab it from the frame. And once the frame is detecting some other faces, it is going to display it on the log that, yeah, the person who is detecting is my name or is it some unknown. So this 0.64 and 0.14 is the confidence level of the detected output. So yes. So I have used a very basic language. The very basic libraries which I have used is a PYNQ overlay. So through PYNQ overlays, I have taken the base overlay as my module. Then I have implemented OpenCV modules. I have used the threading. So threading is used for giving some time for PYNQ Z1 to detect and analyze what phase it is seeing. Then the number of threads is given as 1. Now I have used two path are the two labels and the paths where I have included my base directory. So this is what I will show is my main, what I can say is the trained module. This is where I'm importing the trained module of this output. So based on this, you get this output. You have trained my module. I have trained my module for two peoples. So this is the accuracy. Once you're finding the accuracy greater than 50, it is showing the output. Once it is not detecting that, it is showing that it is an unknown variable. So for every trained face or every trained image, you are getting an output. So I hope the demo part is clear. So this is the label.txt file which we have shown as the label. What is the label which is going to print? Is it my name or is it going to be the unknown person who has included has been captured by the camera? So this Har cascade classifier, it is a standard algorithm which is called as Har cascade or Viona-Jones algorithm. Har cascade classifier is an important formulas of image processing where you can implement lots of AI applications, which is basically used for face detection. Har cascade is a face detection model which we have included in this. So how are we going to recognize my facial detection? So I've used an ONX file and very simple but an pre-trained network. You can say it as pre-trained, but we have trained our module. So I have given my own name. So this is the facial recognition.onx file, which I am passing it to my OS. The threshold point which I have seen is 0.45. So based on the threshold, it is going to detect that the person what it's detecting, is it my name Ashutosh, or is it the unknown person that it is trying to detect. Then once the detection is completed, we have given it a frame buffer. So the buffer is the 1920 into 1080 cross of resolution. The 9020 and 1080 resolution is the active resolution which we are storing it to is. So 1920 into 1080 is the total number of pixels which we have to share in a buffer or a local memory. So based on that, I am starting to detect and I'm starting to implement the face worker code. So this is the function which we have used. So the threshold matching is 0.55. That is the threshold which we have given. And once the threshold label it is greater, if it is less than this particular threshold, it is going to display it as a unknown code. So we have completed our, what we have converted is we have done a color space conversion, a very simple terminology which we can say in this is the color space conversion. We have done RGB to gray format. So once the grayscale image is done, we are implementing a detection algorithm. So based on the detection algorithm, it is going to recognize the feature. So you may see that the inbuilt functions are the functions what we have passed. It is all based on the import libraries, what libraries we have imported in this model. So if the labels or the label is lower or the threshold is lower, it is going to detect it as an unknown. Whereas if the score is greater, then it is going to display it on the red or green value. So if it is matching my threshold, the best score or the accuracy detected, it is going to show you as in the green value, or it is going to show you as the unknown value. So the detection is final. I have implemented a threading option. So this is how I am detecting or implementing a threading option. So why am I implementing a thread is because the HDMI is calculating per frames. It from frame by frame, it is calculating and it is trying to analyze that who is this output coming from. So this output what you are seeing, Ashutosh, is 0.61. 0.61 is the threshold, and my name what you are seeing, this output is based on the decision given by the FPGA. So I have to implement a thread by frame. So it is going to analyze the frames and it is going to give you a particular output. So for this, I have included a base.bit file, the bit file which is configured from the PL side. And I have also given the active resolution as 1920 into 1080 resolution. So from camera, I'm taking 1920 into 1080 as my input, and I'm giving the HDMI output as 1920 into 1080. So the resolution is clear. So with active resolution of 1920 and 1080, it also includes some blanking regions, but you don't have to specify these blanking regions on the PL side. So the monitor's resolution is very clear. As you can see, the monitor resolution, what you see, uh, is completely captured into 1920 into 1080p resolution. So once the camera input and output pipeline is completed, I'm trying to implement a HDMI write function. Whenever the printing variables, what I have included. So the printing values, what I have included in this. So the har cascade classifier is going to give you the value and it is going to keep it in the new frame function. So this is how I'm passing my HDMI output and I'm getting an active resolution of 1920 and 1080p. And the terminal is going to print for every person that it is detecting for every particular time interval. So every 10 seconds, it is going to print you the output. So this is how you can implement what you can say is a deep neural network, and you can train your own module for a high speed resolution. So now I'm going to go back to the presentation because now the concept is completed of how you can do a own facial recognition. Then the concept theoretical part can be started. So as you have seen the demo, so now you can understand what is the facial recognition. So now we can give you, or we can explain you the algorithm part. So what a PYNQ Z1 camera is actually doing is we have connected a USB host to HDMI, right? So what it is doing, it is capturing your input image. The PYNQ Z1 is taking an input image camera. It is extracting the unique facial data. So for every unique face, what you are getting, it is trying to match it from its pre-trained model. The data is then compared with its database. So whatever the output which you saw, what output which you just saw for the facial recognition, it is just a comparison of the pre-trained or the model which we have trained. Based on the comparison, the software is making a decision of yes, the sample is matching, the threshold is matched, and you are getting a particular output of facial recognition. So once the recognition system is complete, so this is the actual flow diagram where you are giving the input image pixels. So for now, our input image is 1920 into 1080p resolution. We have processed it. Then we have extracted the feature extract. So features are what you can say is the neural network. The features what you are trying to implement. For us, it was a Haar cascade classifier. So for this classifier, you can just think that this is a Haar cascade classifier. And based on the database comparison, the face data of like which I have kept my name as Ashutosh. So the terminal or the label is going to print it as Ashutosh. So this Ashutosh name is coming from this face database. So this is just a diagram for this, the prediction, if it is completed or it is a failed. So based on that, you are getting an output image, which is called as known or unknown. So a very simple language, we can just say that this known can be your name. In my case, it is Ashutosh, but in your case, it can be any name which you can give. A person can also be given. And unknown is the face of an foreign. Any foreign face which it is trying to detect and it is not trained can also be considered as an unknown image. So this is the model which you have to train or the data set, and based on the features, it is going to classify and it is trying to give you the output. So another important feature is a deep neural network for object detection. Now, till now, we have discussed on Haar cascade classifier. But now we can also detect on object detection, how you can detect an object, and how can you implement a deep neural network in your PYNQ Z1 SoC or FPGA. So the first part of deep neural network is it is a feed forward network where input layer to output layer without looping back. So without loop back means whatever this process, whatever it is trying to implement, there is no loop back. So for every, the frame detection will be so fast that it will be a feed forward network. So for this feed forward network, you have to create a weighted values. These weighted values can be a pre-trained network. A pre-trained network like YOLO or TensorFlow can be included for object detection, or you can create your own weighted values. So based on the weighted values, it is getting multiplied with the input, and it is trying to give you a two possible outputs. So there is a two possible binary values. Is it true or is it false? So based on that, you are trying to you are trying to get the accuracy of a particular pattern, right? So this is how you can implement a deep neural network. So the most important part in deep neural network will be the training part. So how are you going to get the weight and the bias values of this network? So there are two parts in training part. One is the back propagation and one is the gradient descendant. So back propagation and gradient descents are implemented on the pixel values. For live pixel values, you have to implement a gradient descendant algorithm. So only then the training is completed. So there will be very less difference between the prediction and the targeted output. So there won't be any loss if your output detection is correct. So you are not trying to use a lot of resources in this, absolutely, but the training to the deployment part, there will be a little difference. So whatever the output it's predicting, in our sense, what we showed as a car. So this is the car and this is the person. this has to go through what you can call is the prediction part, and it is predicting the output. So the training part where prediction is less, I mean there is no difference between the prediction and the targeted output, is known as loss function. So this was the active data communication flow which we have included. This is the USB camera which we have given into a USB host, and we are doing the video accessing. So the SOC is same. We are accessing the video, and once the video is accessed, we have included a YOLO architecture. So YOLO is the pre-trained network which we have taken, which is called as YOLO V4 version. YOLO V4 function is used in this, and we are passing a deep neural network, implementing or bypassing a deep neural network based on these weighted values. There is an update on the weighted values, and we are detecting an output. So once the prediction is completed or the detection is completed, you are getting the output in a bounded box by your FPGA. And based on the FPGA, it is recognizing that object. So if your YOLO architecture has this image trained, then it can see any image and it can just show you that, yes, this object is completed, and we are giving you the output in the HDMI format. So the calculation is completed. So what is the input of this deep neural network is the pixel in an image. So what we are passing into this deep neural network is a pixel on the image. So once the video accessing is completed, we are the USB camera, we are getting the pixel values of 1920 into 1080p resolution. We are accessing this video. We are passing it on the deep neural network. So the pixels, once it is completed, there is a data flow or the number of values that can be exchanged between the processing system and the programmable logic. So the pixel values, whatever the trained values, what you have given, there is an interconnection between the PS side and the PL side of the FPGA. So based on that, you are indicating a pattern and the representation. So for this, you have to use a fully connected neural network. So once the network weight is completed and the training is completed, you have to incorporate a fully connected neural network for every neuron in the subsequent layer. So there will be a lots of hidden layers, and based on the output of one layer, it is an input to another layer. So deep neural network is the vision processing unit in your FPGA, using YOLO V4 architecture as the backbone of this vision processing unit. So I guess you can see in this image that I'm showing some input to the camera, and I'm getting output from my prediction. The prediction is DAW. So based on the images what we have given through the FPGA is going to give the result based on the hidden layer output. So the prediction is happening based on this layers what we have shown. So now we can go through the coding side. So we can understand what is the deep neural network and how you can implement deep neural network in an FPGA. So let me stop my screen. I will share it. So yes. This is how you can implement a deep neural network. This is the YOLO configuration, which I'm implementing in this. So there is, again, I'm including some threading function for giving time or giving some delay for the FPGA to understand what is the detected output. So I guess you can start from the YOLO part before we can start the YOLO part. So YOLO V4 tiny configs is the configured values, the config values which I have given. The weighted values is called as YOLO weights, which I have bypassed in this. So once deployment is completed of this code, you can see this is the expected outcome. You can see this is my face. It is showing as person when it is detecting me. This is the camera, which you can see. The camera is there. That is the camera which you are seeing. So based on the camera, it is taking the input of the pixels. It is trying to analyze my features, and it is trying to give you an output that, yes, this is a person which you are seeing, and this is a giraffe. suppose a giraffe, which you can see. So it has lots of object detection patterns is only based on the Coco names. Whatever the Coco names it is trying to receive. Now, suppose I remove this and I keep a person. So based on a person, if I have to give, like, is it going to detect in real time? So there is some detected value or the threshold which it is trying to calculate. It is taking certain time for calculation of that person. And once it is it is trying to analyze that prediction, it is going to display the output as person or giving it as a label. So yes. So you can see that we have, it is trying to detect now as two persons in same monitor. So this person, the accuracy you can see is, how you can see it, this is 0.98, 0.99 and 0.99. So the accuracy of the model is 0.99 for deep neural network. So now I'm going to try to explain you the coding part in the PSI. So there is a config threshold again, like previous Har cascade classifier. I'm using a threshold value in this, and based on the threshold, there has to be loading the model, which is called as YOLO class. I'm giving a read function, so I'm just passing the read function to this. And once the deep neural network, I'm passing or implementing my deep neural network through this YOLO weights and YOLO config values. So this is the main part where I'm trying to bring DNN into the picture. So I'm till now the signal, the pixel acquisition is not completed. So till this point, we are just trying to train your deep neural network value. So now from here, we are trying to get an output layer. So whatever the unconnected or the output layer which you are getting. So now we are trying to pass the function of the output network. So now once the threading is completed and your threading is, you are out of the threading block, you are passing a YOLO threading function. So without any backlog, you are getting an YOLO functions are passed, are the frame buffers or detection output, what you are seeing. So now you can implement a deep neural network from the image. So based on the input size and your input image, there is a output layer which you are passing it or feed forwarding in your deep neural network. So if the frame buffer is not there, you are trying to drop all the old frames. So if the frame buffer is the main part in this, so if your frame buffer is not there, you are telling that you are practically taking the resolution of 1920 to 1080p, and these frames are calculated based on your DNN model. So you are passing cv2.dnn block from image. So now we are passing to the boxes config and IDs value. So what is the boxes? This is the confidence value. What is the confidence of your output? And then you are getting the config threshold. So based on your threshold value, if it is greater than or equal to that threshold value, it is going to create a box. So based on the creating of box, it is going to show you the output, like what is the detected output for this. So the deep neural network is only based on the threshold, and the output is based on the appending or the detected value. So once the YOLO thread is completed, I have passed or bypassed 1920 into 1080p resolution at 24 hertz of refresh rate. Once the refresh rate is completed, I'm passing it out to my HDMI output, and I'm capturing my camera through video capture. So whatever input resolution I'm trying to receive, I'm getting it back as 1920 into 1080p only. So this is how I'm reading my image, and I'm resizing it from frame to frame. Now, once this detection is completed, I am implementing a detection output. I'm passing it as a label. So whatever it is going to detect in real time, and the time frame of each detection, it is going to show you that, yeah, the detection is completed for every 10 seconds. I guess, yes. 10 to 20 seconds is going to detect you the formatted output, and I'm passing my output values in the new frame. So what I'm doing is the pixel values what I have received, I have implemented a deep neural network, I have given a prediction values, weighted values, config values, and based on that, I'm passing my output. The passing of output is where I'm getting a DNN computed value where the prediction is done by the hidden layers. So again, if you see the demo in this, so yes, there is a person in this frame where there is no bounding box. So it is calculating the pixel values. There is a PYNQ FPGA, which you are seeing. There is the USB host. It is giving the 9020 into 1080p resolution, and it is detecting it as a person with a confidence level of accuracy of 0.97. So like that, like you have just seen a giraffe, horse, any pre-trained module of YOLO can be implemented on PYNQ to get the desired resolution output. So yes, let's just start again with the output part or the next phase of our webinar. Any doubts they can be asked at the end of the session, I guess. Yes. Yes. So this is how my timestamp is going to detect you with an accuracy of 0.99. So you can ask like, what are the training sets values? Have you just trained a person? No, you can train a lot of things for now, but what we have used is COCO names. Through COCO names, we are trying to implement only particular set of trained values, and based on that, you can get the desired output. So this is an important architecture value. You are going to understand how you can implement deep neural network in a basic PS side language. So without using a lots of resources, you can just pass it directly and you can just see the YOLO v4 using YOLO function in PYNQ instead of using some peta Linux and using boot.bin. You can utilize all the resources of your FPGA for implementing a deep neural network using a common base.bit file. So the PL side of the bit file will remain the same, but the PS side, how you are trying to write a function for a deep neural network is going to depend or determine what is the accuracy. So the maximum accuracy what we have achieved is 0.98 to 0.99 accuracy based on the threshold what we have set. So now we are going to discuss on the PL side of our FPGA. Now, till now we have discussed on the PS side, like how you can just, instead of writing any code, you can just directly write a PS side code and you can just implement any AI functions. But how can you implement these functions on the PL side? So let me share my screen. So I will now explain the PL side of HDMI instead of PS side till now. So this is the top module which I have, which I am sharing in my screen. So so the PL side of the HDMI physical pin or the PL side is called as transition minimized differential signal, and very important phase of the coding is called as the transition minimized differential signal. This is the actual output in the ping Z1 FPGA, which is based on the schematic. So I'm going to show you the schematic of the HDMI. So yes, this is the transition minimized differential signal of our HDMI. This is the clock and differential clock what you are giving differential data. So D0, D1, and D2 is the differential data of your HDMI function. And this is the TX to RX. TX to RX, which you can do it as a loop back. You can do it a loop back. So before starting, I'm going to just explain what is a transition minimized differential signal. So TMDS can be of two stages, encoding and decoding, are parallel to serial conversion. So for this, it requires an independent TMDS clock, a pixel clock, which you have to generate from your own PLL side, a PLL side. So we have to encode these pixel data live from your video source, and you have to generate a vertical sync signals. Based on the sync signals are the 10 character streams what you're seeing. Then it has to convert from parallel to serial and serial to parallel conversion from 8-bit to 10-bit encoder, which is called as TMDS output. So for every 5 seconds, the ping Z1 goes through PYNQ OS goes through a boot format. So ping Z1 are the transition minimized differential signal. These are the signals I'm passing it directly to the PL side of our signals. So I'm going to show you the output, but before that, I'm going to explain the model. So TMDS value has 10 cross 1 parallel to serial converter of actual pixel clock rate. So encoder to decoder. So this is the input of this TMDS encoder from 8-bit. I'm passing an red, green, and blue channel values, R, G, and B. And based on the R, G, and B values, I'm also getting a sync signals, a vertical sync or horizontal sync. So this vertical sync and horizontal sync and the data enabled channels, what I have showed, it is going to be the input to this HDMI or the pin signals, what I have seen. So once the TMDS is giving the coding from 8-bit to 10-bit encoder, it is going through the OSIDS block. So this is an output serializer to deserializer output or 10 cross 1 converter. Now, after the OSIDS block is completed, I'm completing and I'm showing it as a TMDS output value. So TMDS is the transition minimized where you're giving the positive and the negative channel for both differential LVDS channel for positive, red, green, and blue channel for clock positive and clock negative. So how can I implement a pass-through implement function in an HDMI? Very simple. You can implement a pass-through function. So pass-through function can be implemented by directly connecting the sync to source, a source to sync connection. So this is the TMS transmitter, which I have given as an input to this ping Z1 FPGA. This is the ping Z1 FPGA. I'm giving my HDMI input or the stream input directly to this ping Z1 FPGA. I'm passing my output directly to this HDMI outlaw. So what I have done it on the PS side where you are passing directly the function, you can use RTL side where you can write your own TMDS transmitter and TMDS receiver by using a primitive IPs. So what is TMDS is a two-stage processor where 1 bit of 8-bit into 10-bit of code without particular desirable properties. So I have included an XOR and XNOR operation. So based on the 8-bit to 10-bit, one output will be performing an XOR operation and another output will be performing an XNOR operation. So based on the determine output of the XOR and XNOR, the output will be considered as an encoder because you have just encoded this data bits. And from 8-bit, you are inverting. One part is ones and another part would be zeros. So ones and zeros output, what you are seeing will be helpful on creating an LVDS channel, a low voltage differential signal, where once it is positive, the another channel will contain the negative data. So positive, negative, positive, negative. Based on the serializer, I'm passing it and I'm giving a differential clock and differential data channel. So the pass-through can also be happen if you just connect an HDMI pass-through from source to sync or sync to source. So yes, this is the HDMI RX schematic what I have shared. So the HDMI RX clock N and clock P is a direct connected to or integrated with the PIN Z1 SoC or FPGA. So you have to just directly give this signal to this HDMI, and based on that, you are going to get an output for this. So HDMI TX to RX, I'm passing this value. So this is the actual block data. So how can you perform an pass-through function or implementation in this? This is the source to sync a value where you are passing the blue channel. First data is considering a blue channel. The second block has the green channel, and the third block has the red channel. So all the three channels are going through a separate encoder, a serializer. So based on the channels, every channel will contain a separate encoder, a serializer. And for all three channels, it is going to require a decoder to convert these RGB values to a TMDS data. And again, converting from this RGB to TMDS data. So source to sync connection can be done easily on PYNQ Z1 FPGA through this encoder and decoder format. So this is how where I'm giving the pixel clock, and I'm giving a fixed pixel clock to both the clock channels. So this is the timing diagram of our TMDS. It requires 2-bit extra per color lane. So for every 8-bit per color channel, you are adding 2 bits extra in your color lane and making it as 10 bits. So overall, you're getting 30 bits per pixel. So for every TMDS clock, what you are getting, you are passing a red channel, green channel, and blue channel with 30 bits per pixel value by acquiring one. So the RGB data, horizontal synchronization, vertical synchronization, and TMDS encoding algorithms, the 10-bit data needs to be sent out in parallel as a serializer. So this is how I'm passing the differential data parallelly, all at once, without doing any serial to parallel to serial. I'm passing it a parallel data to this. Again, it is deserialized and it is decoded out. So the control signal, what you're seeing, the CTL0, CTL1, and the H-sync and V-sync, that is an horizontal synchronization and vertical synchronization for frame rate. So the frame is so continuous that a human eye cannot perceive the rate or the speed of the frame transmission. So what it does, it requires a synchronization signal to complete our frame for H-sync and V-sync is necessary. So they have mentioned that FPGA encodes both the RGB data, H-sync and V-sync using TMDS and control encoding algorithms. So CTL is required for the controlling application. So how can you implement what you say this TMDS implementation function in your any Zinc FPGA, right? So you require a DDR functionality. So DDR is called as a double data rate. And you also have an OSRDS2 primitive. So OSRDS is a primitive where it is used for serializer and deserializer of output. Now, that final timing diagram, which is going to be explained, because you can see that there is 10 times, speed will be 10 times. So for double data rate, it is 5 times the clock. So the reason it is 5 times the clock is because it is double data rate. So 5 is for the positive cycle and 5 is for the negative cycle for DDR. So over 5 plus 5 is equal to 10 clock cycles it is going to require. So for every 1 pixel, whenever it is transmitting, the pixel clock, whatever it's transmitting, it is going to generate a TMDS channel of blue, green, and red channel 10-bit parallelly. And it is going to be done continuously. So this is how any industrial standard HDMI pipeline works, is following this timing diagram. So the channel is given directly, and we are passing the streamed values in a double data rate format. So the control data, whatever we are passing, is the C0 and C1, which is going to help you synchronize with the clock. So you are trying to keep the receiver synchronized to its clock with the transmitter clock. So as you are trying to implement a pass-through, both the clock of the pixel clock has to remain same. There is no different clock or not bypassing of the clock in any manner. So this is the physical pin architecture of the HDMI pin, what we see. So the clock pin is the 10th and the 11th pin. This is the clock pin which we are in any HDMI which you use. The channel 0 and channel 1 will be the 7th and 9th. This is the physical pin for 7th and 9th. So channel 1 will be the 4th and 6th value. The 4th and 6th pin is the uh, blue channel. I guess, yes, this is the second channel. So it will be the blue channel, no, green channel. And channel 2 would be the first and 3. That would be the green channel. So blue channel. So R, G, and B. So red channel, green channel, and blue channel, as shown in this, is going to be passed. So the timing diagram, I guess, can be the opposite of this. The green will be the first channel. So red can be the 0 channel, or it can be the second channel. So let me show you the RTL side of this. So So this is the HDMI pipeline which I have used. So how am I going to implement a differential signal? So before proceeding with the coding part, I'm going to show you the output of this. So yes, this is the CMOS camera which you are seeing right now. So the CMOS camera which I have shared. Yeah. So this is the transition minimized differential signal. So you can see this is the FPGA. Can you put the fan? This is the FPGA which I have used. And based on the FPGA, I have given it the CMOS camera. This is the CMOS camera which I have used. The CMOS camera is getting as an input to this HDMI. I'm passing my output through this HDMI port. And based on this clock, what you can see, yeah, if I'm keeping my hand in front of this camera, I'm getting an output in my monitor. So the active resolution of this FPGA, what you are seeing, or the screen, what you have seen, is a 640 into 480p of resolution. Based on a very CMOS basic camera, it can be used to implement a basic RTL functions in your output. So yes, you can, the stream is clear. So as you can see, the stream is too clear. You can apply a histogram equalization, increase the brightness of your code, or you can implement a lot of other convolution algorithms like Sobel edge detection, or what you can say, yes, grayscale imaging. Everything can be done through your CMOS camera. So let me get back to the RTL side before we see the demo. So, so I have used this RTL. This is the RTL for this, which is called as the OV7670 camera, the CMOS camera which we have chosen. This is the input to our model. The output will be the master clock which we are giving to this CMOS. The heatsink is the input what we have given. We are getting 8-bit per pixel as the total values what we have seen. SIOC and SIOD is the I2C protocol which we are giving it to the CMOS camera. So the CMOS camera can only be communicated using I2C protocol. So this is all the physical pins of the camera which are mapped on the general purpose input output. So you can see in the constraints, I will show you. Yes. So this is the IO peripheral, a GA1, the PMOD GA connector, and a PMOD JB connector. So the differential signals what I have received, this is the physical pins of all the OV76 or the CMOS camera for this. And this is the output, the physical pins of our HDMI. So you can see that what I have explained earlier, the timing diagram. This is the timing diagram for this. I have used the TX clock and TXP. And this is the differential clock which I am providing through RTL. This is the differential data what I have shared. And this is the top model. So yes, this is the top model which is mapped. Now let's get deep into the RTL side. So not understanding how you can implement through the TL side, right? So again, you can implement, there are three clocks which I'm taking as an output from based on my system clock input. So my system clock input is 125 megahertz, which I have taken. I'm generating differential clock. So let's go back to the frequency model. I have used the clock wizard or PLL for this, where you can generate your own desired frequency up to a minimum range. Yes. So this is the input frequency 125 megahertz of our PYNQ Z1 FPGA. I have generated 250 megahertz as our TMDS clock, 25 megahertz for your OV7670 camera capture. So camera is capturing at a frequency of 25 megahertz from OV7670 model. I am generating a differential clock based on your TMDS clock through your clock wizard, which is 250 megahertz. So 125 megahertz as an input. So let me go through one model each by each so you can understand the behavior of each model. So what I'm getting inside this model is I'm taking the pixel clock as an input, vertical synchronization and horizontal synchronization. I'm taking the pixel data as an input to this model. And I'm trying to generate an output model of 12-bit per component. So 12-bit per channel means it is 4-bit per component. So red channel, green channel, and blue channel. And I am also generating a write enable signal for this. So this is the how you can try to take the pixel values and convert it into R, G, and D format. So R, G, and D, red, green, and blue channel. So whenever my vertical synchronization is complete R1, my address is resetting. Otherwise, it is continuously incrementing until my particular resolution is completed. I have taken my pixel data as an input and generating a 12-bit per component. So this is how I'm latching or performing and concatenating my pixel values for red, green, and blue channel. And I am passing it on the making it as a 12-bit per component. So this is the model of camera capture. This is the controller part of our CMOS camera. So this is the SIOC and SIOD. So I2C protocol I have implemented in this, and I have also given out to the reset and the power down variable. So I have outing the master clock of the CMOS camera, which is input to the CMOS camera or OV7670 camera model. So based on that, I am generating an SIOC and SIOD signal are the register mapping of my I2C protocol. So the register mapping is based on the FSM or the finite state machine. Our finite state machine is determining how am I going to implement the I2C protocol, and the register values is completely based on the datasheet values. So the output, what you are seeing in this is 16-bit component. So 16-bit component, whatever the values you are seeing in this is based on the write address and write data and the slave ID. So the registers for this is based on the data sheet of the OV7670 camera model. It can be referred online by the vendor, which I has given. And based on this, you can understand that how you can perform a register mapping using the I2C protocol. So this address is incrementing continuously until it reaches the value of this particular hexadecimal. So till then, you have to I2C protocol is necessary to bring an active resolution of 640 into 480p. So based on this I2C protocol, you are trying to determine the resolution of your output camera image. So currently my I2C protocol is based on 640 into 480p. and I am passing this based on my FSM module. So based on the register value and the data value, the right I2C protocol is implemented in this, and the slave address or the camera address which I have given, or the right ID is 42, which I have referred from the data sheet, the 11th page of the data sheet. You can just refer and you can understand that the 42 hexadecimal is the address or the slave address of our data value. This is the register address and the registered data. Whatever you are getting from the register, you are passing it to the I2C protocol. And based on that I2C sender, it is trying to implement the FSM and it is trying to implement the SIOD and SIOC. So serial clock and serial data is configured, and now your CMOS camera is ready to capture 640 into 480p resolution. So we have handled these many physical pins. Now we have to start looking at how you can handle these physical pins. So yes, once the capture is completed and my data is getting as an input from my camera module, 8-bit per data, it is generating a controlled value, write data. Now this 12-bit per component, what you are seeing captured from this particular logic or latched in this function is passed into the block RAM. So the very important part, like how you can use the frequency by just a simple block RAM, and you can determine the write and read function without using any external memory is determined on this particular line. So for every write clock of 25 megahertz, I'm passing my 4-bit per component, total 12-bit per channel, and I am getting an output of 12-bit output. So I'm going to show you the frame buffer for this. Yes. So this is a dual port RAM where you are passing the write and read. So you are writing and reading first. So the total particular 4-bit per component, so 4 plus 4 plus 4 is 12-bit per component. Total 12-bit is going as an input to this module. 307200 is a multiplication of 640 into 480. So if you use a calculator, you will see that 640 into 480 is equal to 307200. So the write depth is 307200 and the read depth is also 307200. So I am writing my values first from first port A, and I'm reading it back as the same depth. So a very basic block RAM is used to determine the flow or the stream of the output. Now, you can see that the read value for this BRAM, I'm reading it on a different clock, whereas I'm writing it on a different clock. So my writing clock is based on the pixel clock, the clock of the OV7670, which is called as 25 megahertz. But my output clock is based on the 250 megahertz. So how am I determining what is the output of the pixel clock? So let's go to this model. This is the main module where you can implement the physical pins of this. So you can see the output of this particular module is a clock P, TXGP, and TXDN. So 3 channel of differential data is getting out, and I am also getting output of differential clock signal. So this is the differential clock signal, this is the clock pixel, and this is the differential. So this is the positive channel, this is the negative channel. This is the positive channel and this is the negative channel. And the input to this module is the pixels which are read from the block memory. So the total pixels which I'm trying to read is 307200. So it's a 640 into 480 intensity values which I'm trying to read it from my BRAM, and I am giving an address like how I have to read it out. So this is a little complex, but I hope everyone understands it, and they can ask any questions if they are feeling uncomfortable understanding this. So this is the video signal generator. I'm going module by module, so you can understand the concept building of this. The video signal channel is where I am generating an MMCM, which is called as mixed managed clock output. So I'm using MMCM, mixed mode clock manager, which is giving you a custom output of differential signals. So MMEM pixel clock is then output which I'm getting from my MMCM primitive. So this is the primitive of MMCM, mixed mode clock manager. So I'm giving my input of 125 megahertz. And based on my 125 megahertz, which I have generated from my clock wizard, it is going to generate a pixel clock differentially through this primitive. So this is the 125 megahertz, which I've given it as my input, and I'm generating a differential output signal. So the TMDS output can be calculated by this clock divider. I have used the clock division, and clock multiplication is not possible, but clock division is definitely possible. So this is the MMCM primitive which I have used, and I have also generated what you can say is a video timing generator for this particular clock. So before going to this, you can see it here that my output, what I am giving. So the pixel clock, what I am receiving from this is the frame address. So once my resolution is completing 480 and it is less than 640, so my once the resolution is completed, the address is going to continuously increment freely without any other hard closure or stopping the counter. So based on my counter, it is trying to increment for 640 into 480p hand resolution. So based on this, I'm generating a 640 into 480p clock. So this is the timing diagram for this. For every 640 into 480p resolution, I'm generating an 800 lines, which has to be counted, and 525 complete screens. So I'm using the TMDS encoder. So based on the clock pixels, what I'm giving as my input, I'm trying to encode it to my differential data channel. So I have used an encoder, which I can see is this is the encoder for this. I'm giving the pixel clock, and based on that, I'm getting 3 differential channels. So if you go to the TMDS encoder part, this is the negation operator which I have used, or XOR or the XNOR operation, to invert my data. So this is how I'm giving my 8-bit to 10-bit encoder and decoder formula. So this is the encoder and this is the decoder part of the TMDS data. This data module is called to generate a TMDS differential output value. So the primitive what I have used, encode red, encode green, is same, but there is a difference when you try to encode it on the blue channel. So once you're trying to encode it on the blue channel, you have to use both the vertical synchronization and the horizontal synchronization. So based on that, it is encoding both the control data, is taking both input, and based on that, it is trying to give you the TMDS blue channel output. So this is the module of TMDS encoder. So based on the internal functions are the 8-bit to 10-bit encoder, it is going to use the TMDS data and TMDS code as the output for this. So once this TMDS part is completed, we are going again to the source part, where I am trying to generate my red, green, blue channel for 8-bit to 10-bit per component. So you can see the input is total 12-bit. So what it will be is this 4-bit per component, 4 red, 4 green, and 4 blue. But once it is trying to reach this model, the frame generation, I'm concatenating it to convert it from 4-bit per channel to 8-bit per channel. So based on my enable signal, or whenever I'm reaching the active area of my video signal, I am generating, and I can completely convert my 8-bit to 4-bit to 8-bit per component, and it is given as an input to this module. So this is the input where it is completely converted from 8-bit per component, and it is going as an input to this. I'm passing the TMDS red signal. So once it is going through this TMDS red signal, it is going to go through the O buff DR. So once the red value, green value, or the blue value, so red channel, green channel, blue channel, you are generating a differential signal using the O buff DR. So differential output buffer is required to generate a single-ended output to a differential ended value. So differential P value and differential N value is going to determine the output in this. So if I program my device, So this is the output of my code, which I have seen, I have shown. So yes, this is the output of the module. And this is the camera which I have used. The camera is integrating, yes, and it is showing me the output for 640 into 480p resolution from PYNQ FPGA. So another code which I can, what the demo of the objective of our demo was a pass through, which I guess we can show you is how you can pass the source to sync transmission. So yes, perfectly you can see the source to sync output with this. Yes. This is the source value, which I have given it as an input to my FPGA. This is the FPGA where I have given my source value or HDMI input. The HDMI output is going to determine the same. So whatever the difference you see, if I show this, you are also getting the output in the output format of our HDMI. So this is also based on an IP integration. Instead of writing an hardcore RTL or writing a OBUF DR, OSIRIS and block, you can just use a direct signal or output signals or IP configurations by simply connecting two IPs, and you can achieve this outcome. Yes. So a very important architecture of TMDS signal. I'm giving my HDMI input as my source. I'm converting it from DVI to RGB format. I'm making the active resolution as 1280 into 720p. I'm giving my pixel clock through this clock wizard, which is 200 megahertz. The converted RGB is given again to the RGB to DVI converter. So RGB is also converting it for this resolution. I'm making a color space conversion, and then again I'm passing it as a HDMI output. This is a constant value which you have to give, which is the value which is called as 1. And once the programming is completed, you can see that the outcome will be similar. So the source to sync connection is completed. You just whatever the stream it is trying to receive from your module, it is going to determine in your output. So yes. So does anyone have any doubt regarding uh, video image processing application and AI application of Ping Z1? Okay, I have Abhay Singh has asked a question. I know he has raised his hand. So yes, Abhay sir, what is your question? Can I get reference paper for this design? Yes, you can get a reference paper of this design. I'm going to share you personally on your mail. So this is actually not a reference. This is a complete IP which I have generated on my own without using any other external source. This is completely done, hard coded from me. So which tool I have used for my model to train? So benefit of doing it on FPGA. Okay, so Sumit sir. So model, I have trained my own model, and we have used whatever the output what you're seeing for person detection. We have used as YOLO V4. YOLO is for object detection, what we have used, and for power cascade classifier, I have used XNet space. Sorry, XNet. It's actually XNet. I've written as YNet. YNet as space. Okay. So yes, another question we have. My research work is on FPGA-based recovery data assays, and I need some more sessions regarding this. Is it possible to have more sessions? Yes, we can give you the session for this, and we actually work closely on research centers for artificial intelligence on FPGA. And the reason we have chosen this board is because the configuration is very easy. You can use an RTL approach or PL side to get the output, or you can use the PSI without trying to configure the PL side. So yes, to program the PL on SoC, is there any open source tool available? Uh, we have a Digilent reference manual, reference manual, but camera integration for what is the benefit of doing in FPGA parallel computing, high speed accuracy, parallelly computing, high speed accuracy, and uh, good resolution of 1920 into 1080p resolution. 1920 into 1080p resolution in APSoC can be achieved. Can you share the entire Python HDL for learning purpose? Mm. Please mail. Help you learn. AI application. I'm working similar project like drone detection. I'm using YOLO V8, and when I use real video to detect, then I'm making marking non-drone also as drone. Any suggestions? So the training is not complete. The training is wrong. If the output is wrong, if you're not getting, means the YOLO V8, I guess YOLO V8 you are using, you can use TensorFlow. The data set data is wrong. So YOLO V8, you can use TensorFlow. But the data set, what you are trying to use can be, what is the capability of hardware, how many cameras can be connected in the process. You can connect two cameras. You can connect two cameras at once, one for accessing from PS side and one for PL side. Okay. So the YOLO V8 Python HDL code, you have to make, you have to contact digital technologies for support on, can assist further. So anyone has any other question? Uh, so I guess Sumit sir is asking like, what have we done? Concept of hardware acceleration used. Yes, so I guess you are referring to some PSO path planning. So we can implement a lot of acceleration can be done based on this. You just have to be very good at uh, IP designs, processor designs, or XI interconnect has to be completed. I'm using VS Code and installing TensorFlow Lite with Python kernel. Will it be possible for real-time application deployment? Yes. This output of person detection is a completely YOLO model. We can also use tensor model, which is called as pip install TF Lite, and you can use it on the PYNQ image to get this output. Output can be achieved as demonstrated from TensorFlow line. So, Sai Pavan sir, I'm trying to make it one thing clear that we have implemented this in ping Z1 image. So we are not using VS Code. We can't use VS Code in this because ping Z1 only supports Jupyter Notebook. So this, there is an inbuilt OS operating system in your ping Z1. It is an inbuilt computer. In that computer, you have to implement this TensorFlow or YOLO functions. So TensorFlow, YNet XFace for facial recognition, and YOLO for object detection. It's not that you have to just use YOLO. You can use mobile net also can also be used for AI implementation. ONX, we have used ONX file and we have converted it and we have trained this model locally. So whatever my name you're seeing in the output has trained locally and tested in the local server. Then we have included it on the PYNQ FPGA. So we have used the ONX file. We have imported that ONX file in our PYNQ FPGA. Then we are trying to implement a neural network. We are trying to see the prediction of our output. Nation. Yes. Yeah, I guess. Working for drone detection, please contact our mail so we can assist further on border deployment. So can I get model train reference doc? Yeah, we can give, like I said, that this model which I have trained, it is not a pre-trained model. I have the facial recognition is trained from our own end. We have trained and we have tested it locally. And once the accuracy was more than 95%, only then we have brought this ONX file into the picture and we are deploying it on the PYNQ FPGA. We can provide support on model training. So model training is a very important concept in AI because the prediction is based on how good your model is trained. So S-phase, Haar cascade classifier, and we have achieved this. So can support our model training and deployment in FPGA. And benefit of doing it on FPGA, I guess I've answered this. We can give acceleration PL side of FPGA. So hardware accelerations we can achieve. Yes, that is true. It can be done using an high level synthesis IP or HLS, and on the based on that we can give an answer like how can you implement a acceleration purpose for this. So yes. So any other questions we have? Yeah, recording will be shared. Drone detection YOLO V8. YOLO V8. We can connect and might face this issue. Okay. So benefit of doing it FPGA parallel computing, high speed accuracy. So best computation speed is a main factor in FPGA. So yes, best computation and high accuracy output. Okay. So I guess we don't have any other questions. Yes, we will share it. Yes, we will share the recording. Recording. So Anup sir, I think you can take it from here. We don't have any other questions. So any other questions, you will be shared the output. You have seen the output and you know how the detection is done from our end, how you can implement the vision processing unit pipeline in your PYNQ FPGA. So the main concept of this webinar was to understand how to implement a vision processing unit from input to output. So for every pixel input, whatever you are getting, how you can detect, implement, apply an inference and get a high accurate output. So we can also use a deep processing unit that can also be used. So yes, the answer to Sumit sir was deep processing unit. I think yes. Yes. Deep processing unit is an important IP which you can use it on the PL side. Deep processing unit in PYNQ FPGA, FPGA for applying inference on the PL side of our FPGA. Applying inference on PL side. Okay. So yes, any other questions?